Hello, and welcome to our session on logic gate configurations in digital logic circuits. In digital logic circuits, the gates that make up the circuits can be implemented into functional designs using a few basic approaches. These are the AND-OR-INVERT, OR-AND-INVERT, or NAND-only configurations. AND-OR-INVERT, as well as OR-AND-INVERT, are straightforward implementations of complex logic functions, but also use a minimal number of transistors in CMOS and other technologies to implement. NAND-only implementations, while they require some Boolean manipulation to come up with, are especially attractive because not only do they consume a small number of transistors, they are also faster than many other approaches to implementing digital logic circuits. Today we'll look at all three configurations. The first configuration is the AND-OR-INVERT configuration, and it consists of a first stage of logic that's AND gates, a second stage that consists of the OR function, and a third stage that consists of inversion. AND-OR-INVERTs can be directly implemented from a truth table to describe a particular logic problem, and at the transistor level can be implemented in a single stage so that the output is calculated within a single clock cycle. Looking at this example here, we have two AND gates, ANDing A, B, C, and D, and one AND gate ANDing E, F, G, and H that are shown here at the beginning of the implementation. Then these two AND functions are ORed together via the OR gate, and finally the inverted bar, the bar over the whole function, is taken care of at the output of the entire function to come up with the output X. We can also implement this function using AND-OR-INVERT configuration. This is the XOR function, familiar from previous sessions. And in order to implement this using AND-OR-INVERT, we'll first put into AND gates A0 and B, and use a second AND gate for A and B0. Then in AND-OR-INVERT, we'll OR those together. And because of the way the configuration is, AND-OR-INVERT requires an inverter at the last stage of the implementation. So to get back to the XOR function, rather than the XNOR function, which is what we have here, we'll need to put the output through another inverter to come up with X. X0 is here, and we'll also have to invert A and B at some other point to come up with A0 and B0 into this function X. So that's one example of how to do AND-OR-INVERT. The important parts are that AND is the first stage, OR is the second stage, and INVERT is the third stage. Now it may seem that these inverters are redundant, but when we go down to the transistor level implementation, we would find out that the NOR function always comes first in transistor level implementations, and if we want to convert NOR to OR, we have to invert the output of a NOR gate in transistor scale implementations. OR-AND-INVERT is very similar to AND-OR-INVERT, with the exception that in OR-AND-INVERT, OR is the first stage, then AND, then inversion. These functions are also readily implemented from a truth table, and they can also be implemented at the transistor level in a single clock cycle or a single stage. This example here, where we're generating Y, involves two OR gates where we OR A and B together through an OR gate. Then we OR C and D together in another OR gate. Then we implement the AND gate in between. And finally, the bar over Y is taken care of by using a NAND gate rather than an AND gate here, which performs the inversion function. So in this way, from a truth table, we can come up with AND-OR-INVERT or OR-AND-INVERT configurations pretty readily. Looking at another example of OR-AND-INVERT, here we have two OR gates, the first one of which will have 3 inputs, and the second one of which will have just 2 inputs. The first OR gate has inputs A, B0, and C, all ORed together in the first stage, and A0 and B0 will also be ORed together in this first stage. Then they'll go through an AND gate. It's required of OR-AND-INVERT that there be an inverter at the output of the AND gate, and because we've now inverted the meaning of our function, we have to go through another inverter to produce the true output out, with the input to that inverter equal to the inverse of our desired function. The last configuration that commonly comes up when we actually implement digital logic circuits from Boolean functions are those that only contain NAND gates and possibly some inverters. Converting a Boolean function to a purely NAND gate configuration requires the application of certain Boolean laws and identities. Specifically, we'll have to use De Morgan's theorem to convert any AND gates and OR gates to the requisite NAND gates. And without going through De Morgan's theorem directly, what's important is that an OR gate whose inputs have been inverted is identical to a NAND gate. So here, in this example, if we invert the inputs to the OR gate and then maintain the meaning of the function by inverting again the inputs to the inverted input OR gate, that allows us to replace now the OR gates with inverted inputs with NAND gates. So here we have one NAND gate, and note that we've now inverted the inputs to the both NAND gates to ensure that we retain the functionality. And C0 and D0 are NANDed in the second NAND gate. The third gate in this system is already a NAND gate, so we don't have to adjust it. And what we have here is a 3 NAND gate function or circuit that's essentially equivalent to that OR-AND-INVERT configuration originally shown for this function y. In this next example, we can also convert this to a NAND gate implementation. We start here by noting that we have AND gates in an AND-OR-INVERT configuration, and we can invert the outputs of those AND gates to get NAND gates, and invert again at the inputs to the subsequent NOR gate. And then we have already 2 NAND gates for the first stage of the implementation, where the inputs to those AND gates are identical to the original configuration. E, F, G, H into this NAND gate. And now we have a NOR gate with inverted inputs, which is equivalent to a NAND gate plus an inverter. Now this NAND gate, according to De Morgan's theorem, is equivalent to an OR gate with inverted inputs. And after we made that replacement, we had to deal with this last inversion before we produced X, which is where the final inverter comes from in this implementation to NAND only. So what we've done here is taken a look at 3 very common configurations for implementing digital logic circuits: the AND-OR-INVERT, OR-AND-INVERT, and the NAND-only configurations. These are very common in implementing digital circuits because they offer much lower transistor counts and greater speed than other logic gate circuit configurations. Well, that's all for logic gate configurations today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.